This next video in the geometric algebra series is going to cover a major geometric fact, which is that two reflections through a vector is equivalent to a rotation. That is, if I start with some vector u, I then reflect through the vector v to generate some new reflected vector called u prime. If I then reflect through another vector called w to generate u double prime, for any starting vector u, this transformation from u to u double prime is equivalent to a rotation. And that's the major fact we're going to spell out in this video. In order to set that whole thing up, what we're going to first do is do a little bit of review of the 2D rotations. We're going to then review the geometric product between two vectors. Then we're going to review reflections. And then we're going to finally tackle this problem of the composition of two reflections. Let's first review what we learned about 2D rotations. Let's say I have some vector v, and what I want to do is rotate v by theta, let's say in a counterclockwise direction, or the positive direction, to generate some new vector called v prime. Again, that angle is going to be theta. And what we learned, I think it was in the first video on geometric algebra, is that v prime can be calculated by taking v and then multiplying on the right by e to the power of theta times big I. And remember what big I was. That was the unit bivector, which is e1 times e2. Now, I could spell this whole thing out in a little bit more detail. What I could say is that v prime is equal to v times e to the theta I, but let me write e to the theta I as cosine theta, just using Euler's formula. So cosine theta plus sine theta times I, or e1 times e2. So this is the way in which we rotate a vector in two dimensions, just by multiplying on the right by e to the theta times I. Hopefully this formula for doing 2D rotations using geometric algebra looks a bit familiar. If it doesn't, check out the first video. Remember too that we were noticing that these formulas were very similar to the sorts of formulas we get out of complex numbers. That is, if we want to do a rotation using complex numbers, that's going to involve multiplying by some exponential. In this case, it's the exponential of a bivector. In the complex numbers, it was just the exponential of an imaginary. Since the complex numbers are commutative, it doesn't actually matter on which side you multiply by the exponential. In geometric algebra, it does matter. So let's say that you multiplied by e to the theta times I on the left-hand side. What's the effect of that? Well, the effect is actually to do this rotation, but in the opposite direction. And I think I asked you to prove in the first video that e to the theta times I times some vector v is actually equal to v times e to the minus theta times I in this reversed order. So these are just some of the major facts I want to review. That expressions that look like this are rotations, and that if you have a exponential of a bivector, and the bivector and v are in the same plane, which is the case in two dimensions, you can switch the order of these two, as long as you stick a minus sign up there in the argument, because we're going to need this fact when we talk about the composition of reflections. Let's also review the geometric product of two vectors a little bit. So let's say I have some vector u and another one v. I take the geometric product, uv. Remember that the geometric product of two vectors can be written as u dot v plus u wedge v. Also remember that u dot v can also be written as the magnitude of u times the magnitude of v times the cosine of the angle in between them, theta. And also that u wedge v can be written as the magnitude of u times the magnitude of v times the sine of the angle between them. I think we covered this fact in the trigonometry video. So I have this scalar times the unit bivector e1, e2. Now, one thing I asked you to show in that video was that this whole thing can be written as an exponential. So I'm going to actually show you that thing here because we're going to need that fact as well. So what I'm going to do here is I'm going to pull out the length of u times the length of v. I'm going to factor it out. Length of u times length of v. So what's left here is cosine theta plus sine of theta times e1, e2. Just for notational convenience, I'll write that as big I. So I have length of u times length of v. Now remember that I squares to minus 1. So I have the cosine of some angle theta plus the sine of some angle theta times some unit that squares to minus 1. Now what I'm going to do is I'm going to write that as e to the theta times I, just using Euler's formula. So what I see here is that the geometric product of two vectors, uv, is equal to some scalar sitting out front, which happens to be the length of u times the length of v, times the exponential of a bivector. Which bivector is that? It's theta times I, or e1, e2. So this is actually a neat way to think of the geometric product of two vectors, and we're going to use this fact as well when talking about reflections. Let's also review how we're going to reflect vectors. So let's say I had some vector u. This is the vector I'm going to want to reflect, and what I'm going to do is I'm going to reflect it through the vector v. Now, the strategy for doing this was to think of u in two parts, as some part, which is projected onto v, which I called u parallel, and some rejected part, which is perpendicular to v, called u perp. Now, when I do the reflection, what I'm going to do is I'm going to keep this vector u parallel the same, and then I'm going to negate u perp. I'm going to draw it over there. That's going to be the negative of u perp. And then I sum the two vectors u parallel and minus u perp to generate the newly reflected vector, which I'll call u prime. So symbolically, what we did is we broke u into u perp, or u parallel plus u perp. And to generate u prime, what we did is we kept u parallel, and then we added that to the negative of u perp. And after a simple computation, what we actually found was that the way to relate u and v was that u prime is equal to v inverse times u times v. In summary, if you start with some vector u and you want to reflect it through the vector v, here's what you do. You multiply on the left by v inverse, and then you multiply on the right by v. So that's the geometric algebra formula for doing a reflection through a vector. This concept of a vector inverse is one of the neat parts of geometric algebra, but remember what that v inverse was. It wasn't really anything mysterious. It was just some vector in the direction of v, that is, it's v divided by the squared length of v. So in the same direction as v, but either stretched out a little or contracted a little. Now what this formula for the inverse implies is that if you select your vector v so that it's of unit length, the length of v is equal to 1, you stick the 1 down there, we get a 1 squared, and what that means is that v inverse is the same as v. And what that means is that this formula for reflection, if you select v to be of unit length, becomes even simpler. It's just the u prime is equal to vuv. I think we've done enough reviewing to tackle our main problem, which is the composition of two reflections. So let me set up the problem. Let's say I have some vector u, and I've got another vector v. Let me reflect u through v. So what I'm going to do is I'm going to look at the rejection part of u. I'm going to negate it, bring it right over there. So the first reflected vector, which I'm going to call u prime, is going to look something like that. So that's the first reflection. The second reflection I'm going to do is I'm going to reflect u prime through another vector. Let me call that one w. So again, I look at the rejected part of u prime. I'm going to send that over there. And then the newly reflected vector, which I'll call u double prime, is going to look like that. So that's what's going on pictorially. Now let's do it symbolically. So we're going to start with u. We're going to reflect it through v to generate u prime. So using our formula, u prime, we're going to start with u, hit it on the left with v inverse, and on the right with v. Now, to get u double prime, what we're going to do is we're going to start with u prime. We're reflecting it through w now, so I'm going to hit it on the left with a w inverse, and on the right with a w. Now, if I just substitute in for u prime, that was v inverse uv. I can also write u double prime as w inverse, v inverse, u, v, w. And just to make this a little bit easier to read, I'm going to throw in some parentheses. Even though the geometric product here is associative, so it doesn't actually matter where I stick these parentheses. What I'm going to do next is I'm going to rewrite w inverse v inverse in the following way, as the inverse of vw, and then u times vw. And this is still equal to u double prime. Now, if you have some experience with linear algebra, you're going to recognize this rule for the inverse of a product, that you flip the order and invert them independently. So let me actually prove this statement, that W inverse V inverse is equal to the inverse of VW. And to prove that, what I need to do is show that W inverse times V inverse times VW on the left and on the right gets me back to 1. So what I'm going to do is I'm going to take this thing and multiply on the left first. So W inverse V inverse times VW. And let me do this computation. So what's V inverse times V? That's 1. So now I have W inverse times W. What's that equal to? That's equal to 1. So that serves as a left inverse. Now let me make sure it serves as a right inverse as well. So I get VW times W inverse times V inverse. What's W times W inverse? That's equal to 1. So this is equal to V inverse. And that's equal to 1. So this statement is true. So this is where we're at so far in our reasoning. We start with U. We multiply on the left by the inverse of VW, and then on the right by VW. So let me concern myself next with this geometric product VW. So this is the geometric product of two vectors. Remember from earlier in the video that such a thing can be written as the length of V times the length of W times e to the theta times I, or E1, E2. Now what's this angle theta, the angle that came up naturally here? Well, that's the angle separating V and W. So let me draw that into the picture. So that's the angle separating the two vectors that we used for the reflecting. So I have an idea of what VW is going to look like. So some scalar times the exponential of a bivector. Now how about the inverse of this expression? Now what number times this will get me back to 1? Now, because that's the meaning of the inverse. Well, I have these scalars sitting out front, the length of V times the length of W. So in terms of an inverse, let's take a guess. How about the reciprocal? 1 over length of V times length of W. And how about the inverse of this expression? What number times e to the theta times I gets you back to 1? Or also e to the 0. Now we might guess that it's just e to the minus theta times big I. And you can verify for yourself that the product of this and this is indeed 1. The scalars cancel out. These two arguments are opposites. Those add to 0. So e to the 0 is indeed 1. Now let me substitute these two expressions into the formula that we generated for two reflections. So we have U double prime is equal to the inverse of VW. Let me just substitute that thing right there. We have 1 over length of V, length of W, times e to the minus theta times I, times U. And then we've got VW, which was this thing here. So length of V, length of W, times e to the theta I. And now this thing here and these two are just scalars, so those can be moved around as you'd like. And in fact, they'll cancel. The length of V's cancel, the length of W's cancel. So what I'm left with is the formula U double prime is equal to e to the minus theta I times U times e to the theta I. That cancellation of the length of V and of the length of W up there is actually quite important. What that tells us is that U double prime, whatever comes out of this composition of two reflections, does not depend upon what the length of V is, and it does not depend on what the length of W is. The only thing it depends on is the angle of separation between those two vectors. And that's because I only see a theta there. There's no length of V, and there's no longer a length of W in this expression. So what I have is that the output vector U double prime is equal to U multiplied on the left by e to the minus theta I, and then on the right by e to the plus theta I. And the last manipulation I'm going to do is I'm going to take note that U and this bivector I are on the same plane. So I'm going to do what I was talking about in the beginning of the video. I'm going to switch the order of these two. But remember what I have to do. I'm going to have to stick another minus sign up there in the argument. So what I have is that U times e to the minus theta I, or just plain old plus theta I. And then I have this extra e to the theta I out here. That's still equal to U double prime. And I'm going to multiply these two together. And what I get finally is that U double prime is equal to U times e to the 2 theta times big I. So what does this mean? What this means is that the overall effect of transforming U to U double prime by reflecting through V and then W is the same as rotating by 2 theta, where theta is the angle of separation between v and w. And that's really the conclusion that I wanted to draw in this video, that we can generate this formula, both this formula and also this formula, where we have some starting vector which gets sandwiched between two other exponentials, and this other formula, which in the special case where the bivector and the vector of interest are in the same plane, we can generate this other formula where it's just being multiplied on one side by the exponential of a bivector. So these two formulas, and formulas that look very similar to these two, are going to show up over and over again in our discussion of geometric algebra. And what I really want to do, I want to show this in the special case of 2 dimensions, just because it's easier to draw and I think it's easier to understand. And it provides a nice intuitive base for understanding higher dimensional rotations. So let's do a little bit more philosophizing about what we've discovered in this video. So we saw that if we just pick any 2 vectors as the vectors through which we're going to reflect, let's say this first one is my vector v, and the second one is my vector w, just picking 2 random vectors. These vectors have some angle of separation called theta, and it doesn't matter which other starting vector you pick. Let's say that vector is u, or that vector could be u, or whatever. The overall effect of first reflecting through v and then reflecting through w is to rotate the starting vectors by 2 theta. And remarkably, it doesn't matter where these 2 vectors v and w are pointing. The all-important factor is their angle of separation. So if I wanted to generate a rotation by, let's say, theta, I could think of that as just picking any 2 vectors, let's say that one's v and that one's w, which are separated by theta divided by 2, half the angle that I want to rotate by. Why half the angle? Because it's going to end up being doubled when you do that composition of 2 reflections. So you just pick any 2 vectors, and again, it doesn't matter what their length is. Just pick any 2 vectors which are separated by theta over 2. I could pick those 2 vectors. I could have picked those 2 vectors as v and w, just as long as they're separated by half the angle that I want to rotate by. So we've got this knowledge abstractly, but of course it's important to think of some concrete cases just to convince ourselves that this thing is actually correct. So what I'm going to do is I'm going to pick the specific example of a counterclockwise or a positive rotation where theta is going to be 90 degrees or pi over 2 radians. And I'm going to pick 2 vectors which are separated by theta over 2. So that means those 2 vectors are going to have to be separated by pi over 4 radians. So what I'm going to do is I'm going to pick 2 arbitrary vectors which are separated by pi over 4. So let's say that vector is my first vector of reflection, called v, as we have been doing, and pick the second one to be that vector, which I'll call w. And these 2 are separated by pi over 4 radians. And now what we know abstractly is that if I do successive reflections, first through v and then through w, that the end result should be a rotation of that starting vector 90 degrees, or pi over 2, counterclockwise. Of course, I can't draw in all possible starting vectors u, but let me draw in a few special cases just to make this whole claim plausible. For my first special case, let me pick a vector that's in the same direction as v. I call that one u. Now, since u is in the same direction as v, reflecting through v will leave this vector unchanged. And next, I'm going to reflect this through w. So I look at the rejected part of u. That's going to go over there. Let me draw on that vector there. This angle and this angle are both pi over 4, which means that the angle from the starting vector to the end vector is going to be, indeed, pi over 2. So that's one special case, where that is indeed a rotation by pi over 2, counterclockwise. Another special case I'd like to do is a vector in the direction of w. So let's say that's my starting vector u. First, I reflect through v. So I look at the rejected part. So that rejected part's going to look something like that. And that's going to go all the way horizontal. So that's going to be u prime. And finally, I reflect through w. And the end result of that, since w is completely perpendicular to u prime, is it's going to flip the direction. So that's my end vector u double prime. So you can see that the overall effect from u to u double prime is indeed a rotation by pi over 2 counterclockwise. Those are just two special cases, and it's actually quite a bit of fun to bounce these vectors around like this. So I encourage you to play around with some other examples, and also to convince yourself that this choice of v and of w was totally arbitrary. The important fact was that they were separated by pi over 4. I could have just as well chosen some vector like this. Let me have that be v, and let this other one be w here, where again these are separated by pi over 4. This angle of separation is the important fact, not where these particular vectors are or how long they are. And that'll wrap it up for this video. Thanks for watching, and stay tuned for more geometric algebra. And of course all the obligatory YouTube stuff. Subscribe to the channel if you like it. Like and comment on the videos, blah blah blah. Hope to see you again.